We'll go ahead and start. I've got a timer set up because I have a tendency to run long, so I'll stop myself and I'm going to allow time for questions, etc. And I'm Ray Simar. What I want to talk about today is some work that we've been doing to create some DSP extensions, new suite of benchmarks added to the Imbench benchmark suite. And in particular, these are several students we've had working on. Andrew this semester, Daniel, Jennifer Heller, who've really done a lot of work over the last several semesters. So I'm going to give you a little bit of background about what Imbench is to kind of give some context to it, and then talk about what our objectives are with these benchmarks. So what you'll see is they're going to set a constraint on the way we're going to look at this problem. And you'll see it'll impact how we do benchmarking. We think these can be used in the architecture development phase of projects, and it can be used for benchmarking compiler performance as well. And to kind of bring all that into focus, I'm going to pick one DSP benchmark, and it's the FIR filter. If you've never seen it, never seen one of these, you'll get it pretty instantly. But I'm going to show you what really goes on under the hood as you try to put one of these together. And it's not just about how fast you can do multiply accumulates. There's more to it than that. And then I want to talk about some next steps. We've started reaching out to people to get more people involved in this effort. And just in the Imbench in general, that is true as well. Okay. So Imbench, Jeremy Bennett, who's here, is one of the co-chairs, and Dave Patterson lead this. And it's been academic and industry colleagues meeting, working on benchmarks targeting the embedded space. And it's a little bit of a replay of sort of the spec mark kind of scenario. The idea, it's about 20 real programs rather than one synthetic program. And the other thing is the code is all available, it's free, it's shareable, there's no licensing kind of arrangements. And the idea is to write the code so it's easy to port to new platforms, to new microprocessors, microcontrollers, high-end, low-end. Now, what Imbench will do is report a single performance number, sort of like if you recall the spec marks, where you could have a spec mark number, but you could then look under that number and you could see how all the benchmarks performed. The other thing is the team has started to report on code size, which is very important in the embedded space. They are furthermore looking at developing benchmarks for issues, again, from the embedded space about interrupt latency, context switch time, which is related to that. So there's a lot of richness to the kinds of things that Imbench can look at. It's already been being picked up in places. I've talked to some people that have used it. We have seen some reports have popped out at the different conferences of people using it. You can, I'll go over a little bit more. You can go to info@imbench.org. You can email that. You can get on the list. You can go to imbench.org, the website. You can sign up, and you can kind of see what's going on there. Here's just a quick snapshot of the suite. And the big thing I really want to highlight is sort of what's over here. What Jeremy and Dave and the team did is they looked at kind of the loading on the processor. So they picked this suite of benchmarks to look at, is it branch intensive, memory intensive, compute intensive? And if you go to that URL, you can get to the GitHub, you can get all the source code, you can see all of this. So what are the DSP benchmark goals? We don't want to have one number. We want, though, our DSP benchmarks to represent what is a reasonable implementation of a DSP function. We want someone in industry or someone who does research in DSP to look at this and go, okay, this is representative, all right? All the code will be shareable, nothing's proprietary. The other thing, DSP benchmarks can be performance intensive. We're writing them to be architecture agnostic. Because they're performance intensive, you will see implementations of functions where they're very, very tuned to an underlying architecture. We're not writing benchmarks like that. So we don't want them to be biased. We want them to be easily portable, but they still have to be representative. Okay, they have to when you look at the FIR, you should be able to look at it and go, that's a FIR filter. The other thing is we're writing the benchmarks to be scalable, and I'll talk a little bit more about what that's going to mean to us. And you will see they're all written in C, and so they're going to lend themselves to doing things like analyzing compiler performance, like how good does a compiler do on this benchmark and extracting the performance that's available. I've talked to a number of people in the industry about what it would take for the DSP benchmarks in particular to be useful to them. And the trick is across the embedded space, people have a lot of different operating points. Some people do very low order filter, very high data rates. Others are very large filter, like, for example, adaptive filter, echo canceller kinds of things are often very large filter implementations. Cost-sensitive applications tend to often be fixed point, but floating points becoming increasingly common, all right? So we want our benchmarks to be scalable. We want to be able to do things like vary the number of coefficients, the length of a filter. We want to look at how many samples you process at a time when you run the benchmark. We want to look at fixed point, floating point. We're going to cover all of those over time. Now, for the Imbench suite, we'll pick a few typical implementation points. Maybe a small FIR, maybe a large FIR. And that will help us support our score. But the idea is you should always be able to pull down our code, look at our code and say, okay, I need to run a longer filter or I need a smaller block size. And you should be able to dial those parameters in, compile it, and run it yourself. The other thing is it turns out from RISC, we do a certain amount of work with other universities and research going on in architecture. And what architects need is they need benchmarks they can scale up and down to kind of stress their architecture. They need to be able to explore different levels of parallelism, the data types, do a memory hierarchy analysis. How much data is going to be in the register file? What's going to reside in like local memory? What's going to be in off-chip memory? Looking at all those kind of things. And the other thing is people doing SoC designs, if they can use the benchmark in their SoC design simulation to test out the algorithms in context is a big help. So Jeremy put this together, and I think it really summarizes the key points. Imbench has got to be free, easy to port and run, real representative programs. It's got an organization that supports it, and we report a single summarizing score, but we also give you kind of details under it. So let me talk about the DSP benchmark, and I decided to show you how one of these is put together. What you're going to see is there's some common data structures we'll use in DSP. There's some common algorithm details that pop up, and I'll mention a little bit about ways you might optimize this stuff. So here is a finite impulse response filter. We've got an input X of n that's going to come in. Sometimes this is called, sometimes let's say we've got M 0 to M, so it's an mth order. That means if it's 0 to M, there's M plus 1 filter coefficients for this. Here's the equation for it. And so on the left-hand side, you might recognize this as convolution. But if we kind of unroll this and look at this, it's pretty straightforward. The output of the filter is based upon the current inputs and past inputs weighted and summed, okay? So nothing too complicated there. Now, to help me in my presentation, this is also known as convolution, which immediately scares people. But for those of you familiar with 3 blue, 1 brown, the channel, to help me with my presentation, I view this, he did this for me. Grant Sanderson, just a few weeks ago, has got a great little YouTube video called But What is Convolution? And then when you walk through it, you will say, oh, that's the FIR filter Ray showed us when you look at his presentation. The other thing is, as we're doing our notation and describing these benchmarks, we're going to follow Oppenheim and Schaefer, which I was talking to someone earlier, is Oppenheim and Schaefer are to DSP what Hennessy and Patterson are to architecture. Okay, they're the two people there. So here's the way it's going to look. What the benchmarks will do, they will use what we'll call a filter instance. And the filter instance has, as parameters, the number of filter taps, the number of coefficients, the order of the filter. Then we will actually have a pointer to the actual values of the coefficients. And then you'll see we will have to have a state variable, okay? A FIR filter is something you can run and you can call again with new data. And so it has a certain state it must carry around with it. So we'll see how that works. This structure of coefficients, filter state, order of the filter is very common, not just across filters, but also things like fast Fourier transforms. Lots of DSP functions sort of have this sort of feel to them. Now, in this case, we will see we're going to store the coefficients in what we'll call reverse order, meaning h of 0 is at the most significant, the highest order address. H of m is at the lowest order address. When we call the functions in our benchmarks, the way these will be set up is we'll create the instance, we will call the benchmark, and we will time that. And so when we call the function, what we do is we pass into it a pointer to that filter instance I showed you. We pass that in, and we pass in the input data, the data we're going to filter. We're going to pass a pointer to where the output data will go. And the other thing that we'll have, and this is an important scalable parameter, is the block size. Block size is how many samples are you going to filter at a time. I'll show you an example of that. So you can kind of see how these are all matching the parameters we want to have. So this is our state array or our state variable vector. And what we are going to have for our filter, we're going to have the past inputs. That's what the FIR is going to work. And we're going to have a block of new inputs. This variable is basically, this storage is number of taps plus the block size minus 1. Think of this as this is a vector that we need to keep around. All right, so it has ramifications on the data size that we'll have to use with this filter. Here's the 4 steps. We're going to initialize the filter. We're going to input a new block of data. We're going to filter the block of data, and then we'll update the state variable array. So our benchmark timing will basically generally cover steps 2, 3, and 4. All right, so we're trying to illustrate here what's going to drive the performance of this kind of a benchmark. So we'll look at the data structures, and I'll show you a little pseudocode that describes the different operations. So here's the first step. And I'm going to carry around the filter coefficients here so we can kind of think of them in respect to this state array. The first thing we have to do, we've turned on an FIR filter. We're going to start doing the filtering operation. We just said it depends on previous inputs. There are no previous inputs. We're just using it for the first time. What you have to do is initialize the past state to 0, okay? This is actually for filters, especially, well, for all filters mathematically, but especially the infinite impulse response ones in general, it's a mathematical requirement. It's also good practice. It's a variation on the uninitialized variable problem, okay? If you don't initialize these, you will not be able to guarantee what result you're going to get out. Then what we do is we get a new block of data, and that new block of data is going to be sitting right here. So we're going to call it, and we're going to say, we're going to give you 32 pieces of data. We want to process those. And then the code I'm showing you down here is really just us reading from that source and putting it in that state variable. Now, we're to the point where we finally get to filter something. So here's what it's going to look like. These are the filter coefficients. I'm going to take these filter coefficients, multiplying them by past inputs to the filter, sum them up, and that'll give me the output y of n. And I'm going to run you through like a few steps of this. Hold on. And I start with j equals 0. And every time I do this, I'm going to run through all of these taps. Now, if I stop this right here, this is an example of a FIR filter that's calculating one output value, okay? But what oftentimes people will do, and it doesn't make sense in all cases, but it's one of our scale parameters, they will run through several blocks of data at a time. And what ends up happening is that the coefficients, you can view, they're sliding across, doing the multiplications, all right? And you can see in this inner loop right here, here's the multiply of the coefficients times the state summed up. That's your MAC. But as we're moving along, we're going to process that whole block. Once we're done with that, what we do is we take the last nt minus 1 samples. This will be the last samples the filter saw. We're going to take them, we're going to copy them down into here. They're going to become the initial state for the next time we call the filter. So what ends up happening as we look at this whole thing, the innermost loop is certainly multiply accumulate intensive, but we just don't, that's not the only thing we spend time in. There's a loop that has to take the input data and put it in the right location. We have a loop to update the state variable. So all of those other loop-based operations besides the multiply accumulate will enter into the benchmark. And there's some very important data structures, okay? Just to kind of summarize, we've been doing this at RISC, been looking at it for a few semesters. We've reached out recently, the folks at Rose Holman, Wayne Padgett, Mark Yoder, Daniel Chang, Chris Miller are joining the team. If you want to get a sense of the kind of benchmarks we could do, go to ARM's CMSys DSP library. It's a great set of APIs. Now, the code is all optimized for their processors. But to give you an idea of the kind of tasks and things we want to do, it's really great. What we'll do as Imbench is we'll kind of be the gatekeepers. Let's say you go decide to write something, we'd love it, but we'll be kind of the gatekeepers. My students, we've kind of got dibs on the FIR, IR, and FFT radix 2, which are sort of, if you cook, they're sort of the mirepoix of DSP. They're like the three benchmarks that are really important. But if you're interested, reach out to me. Dave and Jeremy have been a big help in us getting this together. Jennifer Heller, she's now at Cirrus. Daniel, he graduated, he's at Trellis. Andrew's graduating, he's going to Nye Technologies. We've got another group of students coming along. And really credit to Sydney Burris, who taught me DSP and passed away, not because of COVID, but during the pandemic. And he would love what we're doing here today. So if you're interested in doing anything around this, feel free to reach out to me, just email me, etc. Okay? So it's a lot of stuff. You should be able to go open up the PDF and click through the filter. Click through the slides and you'll see the filter go like that. Any questions? Any questions? Yes? Oh, it's a great question because so we're going to have it as a parameter. When we pick an instance for Imbench, we will have a value for block size. And it's a great question because what's important about that is if the compiler can know at compile time the block size, the order of the filter, optimizing compilers will optimize the death out of that loop. Right? Because they know all those parameters. Yep. That's a great question. Any other questions? Okay. So if you have questions afterwards, I'll be around. You can email me, reach out to me. Okay? Yeah. Okay. So we've got a little, Rice and Berkeley have been looking at some DSP extensions to the vector ISA, and Chris has done a great job leading that effort. And so we teed this up, and the FIR was one of the first ones they wanted to look at. So they've been losing some of these, and that's where they do some of the test of, with the vector machine, the question is, how do I get coefficients into the in the vector register file, versus in the memory and the hierarchy? And those are really good questions. And so that's our goal, is to, as then the FIR, the IR, and the FFT is notoriously bad for breaking architectures, use those as test cases in that architectural development work. Yep. Anything else? All right. Thanks, everyone.